All right, so thanks for coming to my talk. Today, I'm going to talk about handling inline assembly. So first, a little bit of myself. You can just call me Min. I'm currently a PhD student in UC Irvine. And I'm also the co-owner of Mtg backend. And actually, I published a book earlier this year, which I will briefly mention at the end of this talk. So today, we're going to talk about how inline assembly is handled in Clang and LLVM. Let's talk about inline assembly first. Inline assembly is a technique that allows programmers to embed native assembly string into C and C++ program. Here is an example C++ snippet. We can use the following syntax to write an inline assembly statement such that the enclosing assembly string will be inserted into the final assembly code of the entire function with little or no modifications. So why do people do that? The first reason is performance. Sometimes a programmer wants a really specific instruction to boost their performance. And similarly, when we're writing an operating system or a firmware, some of the feature just does not exist in high-level language. And finally, compiler optimization is really conservative about inline assembly statement. So usually programmer will use the inline assembly statement as a barrier to prevent compiler optimizations to move instruction across this statement. Let's take a look at this inline assembly statement. The first thing that's spot on is the assembly string. And in this assembly snippet, the final result is stored in the ESI register. But in many cases, we don't want to store the result in a specific fixed register. Therefore, we can use the following syntax to ask the compiler to put the result into the out bar C variable and replace the placeholder %0 with the real location of out bar. Another thing we notice here is the equal R string, which is the operand constraint. Operand constraint is a way to tell compiler what kinds of operand should the placeholder eventually be replaced with. For example, here, R means register. That means when compiler trying to figure out what resource is for this operand, a register is allowed. So in this case, ESI is illegal. But the compiler is not allowed to allocate a memory operand as shown here, the EBP -8, to replace the %0 placeholder. Of course, there's many kinds of operand constraint. In previous pages, we see a target independent constraint where R means register, I for immediate value, and M for memory operands. There are, of course, target specific constraint. For instance, in x86, a character means one of the registers here. And operand constraint can also be multiple characters. For instance, in M68K, CI and CJs are multi-character constraint string for regarding constants. And in previous page, we also see the equal sign. This is the constraint modifier, telling that this operand is an output operand. And similarly, plus means that this operand is both an input and output. And with output operand, of course, we also have input operand. In this case, the inline assembly snippet will take a value from an invar C variable. And of course, you can also use like operand constraint. So in this snippet, we can find that the value inside EBP is modified. So we need to use a clobber operand to tell the compilers that, hey, the value inside this EBP has been modified inside the assembly string. So please don't allocate EBX for other usages. For more syntax, this webpage is a really good reference. So how does inline assembly is handled inside a Clang and LLVM compilation pipeline? Well, actually, in most of the cases, it is not touched at all. So in most cases, the compilation pipeline will just pass the inline assembly string down to the rest of the pipeline. What makes this a little bit more complicated are the operands. So the compiler needs to glue this inline assembly operand with the surrounding code and also conform to the constraint string attached on each operand. And this involves a lot of target-specific logics, means that backend developers need to implement a lot of callbacks to express the target specific stuff or informations. And these callbacks are scattered throughout the whole compilation pipeline. And unfortunately, there's only a little and to no document for this part. So the goal of this talk is first, of course, learning how inline assembly is handled in Clang and LLVM. And more importantly, serve as a simple guideline for backend developers to add inline assembly support for their future targets. So since we're talking about implementing target-specific logic throughout the entire compilation pipeline, here is an overview. In Clang, we're going to do some validation, but here we're only doing some really simple validation. The real validation will happen in the lowering stage, which we not only do the validation, but only doing some lowering if needed. And finally, in the ASM printer, we print out the operands. Let's talk about the first part. In Clang, we're going to override one of the function inside target info. Target info is a class where each target needs to provide information by overriding functions. So the function we're overriding here, taking a string from Clang, which is a constraint string. So Clang will ask in this function, hey, whether this constraint string is valid. And we need to return the answer by the return value. Here's an example. In M68K, the A constraint string means address register. So first, we're going to return true to tell Clang that, hey, this is a valid constraint string. And in addition, we also use a set allow register to provide heuristic to Clang saying that, hey, this is actually a register operand. Similarly, we can use a set require immediate to provide a heuristic that's to say, J constraint string is actually an immediate operand. In addition, we can also provide the value range. However, the value range heuristic is kind of limited. So here's an example of using the J, which stands for the constant sign 16-bit integer here. But here we use the X variable, which is apparently not a constant and it cannot fit into a 16-bit integer. So this snippet is wrong. However, if we only run the front end, it didn't give us any error message. And that is because Clang is pretty permissive on this kind of immediate value validation. You will only raise an error if it's 100% sure the value is out of bound. Of course, eventually the backend will catch the error. So that is basically all the essential thing we need to do in the Clang. Now let's look at one level below into the LLVM IR. In LLVM IR, inline assembly is represented by the really special call instructions. In these call instructions, the assembly string is preserved. And the inline assembly operand is modeled as a function argument. But just note that the placeholder syntax is slightly different. Instead of using %, we use a $sign. Finally, clobber operand information is also preserved. Let's bring us to the next level. The second part of the talk, I'm going to talk about the lowering. As we see in the previous page, in LLVM IR, inline assembly statement is represented by a special call instruction. In this talk, I'm only going to cover the selection deck itself. And in the selection deck, inline assembly is represented by a special selection deck node. And in machine IR is represented by the special instruction. What all three representations listed here in common is that all of them preserve the inline assembly string. And more importantly, the inline assembly operand is modeled as either a function call argument or an operand for an instructions. In this part of the talk, we're going to deal with these operands by validating them and lowering them if needed. The first thing we're going to do is to classify individual operand constraint string. The function we're going to override here is get constraint type in the target lowering. Here we're going to return an enum values. So for instance, if this constraint string is a register operand, we're going to return this C underline register class. And this is for immediate value. And this is for the memory operands. And this includes some special addressing modes memory operand, like the capital Q in ARM64. And if you don't know, just return C other. This function is a really important function that dispatch rest of the workflow. So for instance, if the Cogent framework see the C register class return value, it will use this function to lower the register operands. For immediate value, it will use this function to lower the operands. And the memory operand is slightly different. It will go through another layer of triaging. So first go through this, this function. And finally, the real lowering will happen on this select inline ascent memory operand. In the rest of the talk, we are going to override in all this function that you see here. First, let's talk about register operand. Here we're dealing with getReg for inline ascent constraint under the target lowering. The purpose of this function is to tell the Cogent framework what is the acceptable register to pick for a given register constraint. So the return result will be a pair. The first element in this pair is if this register constraint is corresponding to a specific register, you put it on as the first element. If you don't care, just put a 0. In that case, the Cogent will pick a register from the register class designated by the second element of the return value. Let's look at an example in M68K. Recall that the A constraint string is represent an address register. But here, we don't care which address register you pick. So we put 0 as the first element and put the AR16 red class as the second element. AR16 red class means the register class for address register. And the reason we use AR16, 16-bit, because from one of the function argument here, VT, we can note that the type of this operand is a 16-bit integer. Another example is in x86, where YZ specifically means the first SSE register, that is the XMM0. So here we put XMM0 as the first element. Let's take a look at the immediate operands. Here we're going to override lower ascent operand for constraint, also in the target lowering class. The purpose of this function is to validate the prospective machine value for an inline assembly operand suggested by the Cogent framework, which is the op function argument we can see here. And it needs to even lowering the operand if needed. Here's an example of MCCAK. So again, we're going to take a look at a J, which means a constant sign 16-bit integer. So first, we check the op function argument to see whether it is a constant SG node. If it's true, we look at the value. And we check again where this value can fit into 16 bits. If true, we just use this op as the outputs results. Finally, we're going to look at the lowering memory operands. And again, there's another layer of triaging happening here. So first, let's look at the get inline ascent constraint function we're going to override. The input argument into this function is still the constraint string. What it returns is an enum that describes the desired way to handle this constraint. For instance, constraint underlying M means that the given constraint string will be handled as the same way as the generic constraint string M, which represent memory operand with no specific addressing mode. If your constraint string requires special handling and thus doesn't fit into any of the existing enum value, you can also add your target specific enum into this collection, like the constraint underlying capital A and capital Q. For instance, this is a RISC-V implementation for its target specific constraint, capital A. So it simply just do a one-to-one mapping from the constraint string capital A into the enum value constraint underlying A. And after that triaging, here's the function that really lowering the memory operands. Select inline ascent memory operands in not target lowering, but selection deck I cell. The purpose of this function is similar to the function that lowers immediate type operand, as we saw earlier. Validate the prospective machine value for an inline assembly operand, in this case, the op function argument, and lower this op if needed. Let's see an example of constraint capital A in RISC-V. Note that instead of inspecting the constraint string directly, the constraint ID function argument of select inline ASM memory operand function we're checking here is the enum value returned from the previous callback we override. And here, RISC-V only do the validation and just simply say, hey, if this is constraint A, we admit it, and we just put op as the output results. So it only do the validation. A slightly more complicated example is x86, where memory operands might have a complex addressing mode. So here, x86 is not just doing the validation, but also doing the lowering. So here, for a given op, which is a memory operand, it borrows the hands from the instruction selector to lower this operand into 5 other SD node or SD value, and use this 5 SD value as the output result. So it's basically a one-to-many mappings in contrast to RISC-V. Finally, let's take a look at the ASM printer. So the ASM printer will take in a machine insert and it's going to print it out. So for most part in the inline assembly string, you can just print it. What it needs some help is the operand. So here we're going to fit the operand and replace the placeholder here. And in this case, we want to print an immediate values. But immediate value in M68K, which we've shown here, need to be prefixed by a pound sign. So we cannot simply just put an 87 to replace the $0 placeholder. Therefore, we need to override two function callback inside ASM printer. The print ASM operand for non-memory operands and print ASM memory operands. And since both of them has an identical function signature, we are only going to look at the non-memory operands one. Here is an example of M68K, printing the non-memory operands. So first, the op_non function argument tell you which the index of the operand the ASM printer want you to print. So it just use this index in combination with the machine integer to first get the machine operands. And from here, it can note the type of this operand. So if it's a register, it just prefix that with a percent sign. If it's an immediate value, it just prefix that with a pound sign. And that's basically all of it. So this wraps up our talk today. Of course, we only cover the essential callbacks. We need to override it and the roadmaps you need to do to support inline assembly. There are, of course, lots of advanced topics, including some advanced inline assembly syntax. For instance, the ASM dialects. Like if you're x86, there are AT&T and Intel dialects or variants, and other things that you can actually turn inline assembly into LLVM code if feasible. So thank you for listening. And here, I'm sorry, I need to tell you again, my book is on sale, so feel free to use the promotion code listed here. And thank you for listening. I'm happy to take questions.
Thanks, Min, for this great tutorial and introduction into inline assembler in LLVM. For the audience, please post your questions on the website, and we'll look into answering them. As we're waiting for questions, I have one of my own. I think for somebody who is new to writing inline assembler, the constraint strings can be a bit perplexing. And so I'm wondering if you have any pointers to what the best documentation is to get started on writing correct constraint strings, so you don't run into surprises when your code is compiled and optimized.
Correct. So actually, can we show the slides? Because I think there's a slides. Oh, thank you. let me, oh, here we go. Yeah, so this website from GCC. So the problem is that the C and C++ standard only have one line regarding inline assembly. So that is absolutely not useful. So actually, most of the document is on the GCC website regarding the, including all the constraint string. So that is a good resource. But actually, when I'm working on inline assembly, I also look into the GCC's source code. So in GCC's source code, under each target is simply called the constraints.md, the machine description. It's like the TD in GCC. So in there, you can see not just the description, but also how GCC validate each operands. Because sometimes actually the documentation will have some mismatch, either outdated or simply it forgot to write, like have some mismatch with the real GCC validation. So that is also a good place to look at how constraint string really means.
And if I'm a backend author and I need to define new constraint strings for my architecture, is there a good place to synchronize with other compiler authors about using the same constraint strings?
So usually we won't touch the, usually we won't touch the target independent constraint string because that will affect most parts. But yeah, if you want to add target independent constraint string, yes, you need to synchronize with other backend developers. But if you just implement it for your own target, normally you don't need to do that. Yeah. I was going to say it will violate. So if I was going to say adding a target independent constraint string will violate the standard, but again, actually the C standard doesn't say anything about target independent constraint string. So that is, I feel, kind of amusing. So you really need to talk to other backend developers or even GCC developers.
I have a question from Basil. When expert users who think they should write inline assembler, should they?
Oh, you mean as an expert? Sorry, I missed the first part.
So I think the question is, when should you write inline assembler, and what are situations where it can actually be avoided to write inline assembler, and you should be using something else that is more portable instead?
Yeah, so I think one of the pages showing the use cases of why people writing like inline assembly. So I think the first one, the performance, is the most common one. But should we avoid writing inline assembly? Kind of, if you want your code to be portable, and some common substitution will be intrinsics. But even intrinsic is kind of too low level. For instance, the SSE, the intrinsics provided by Intel, those intrinsics are usually one-to-one. There's no abstraction layers. So I don't know other alternatives to avoid writing inline assembly statements. Yeah, maybe propose a new language features or something. Oh, or like pragma. Like if you want some really special stuff, you just propose a new pragma or attributes, something like that.
Thank you.
Yeah, thank you.
Well, I think we're almost running out of time. So thank you very much for
the
tutorial. And I hope everybody has a great rest of the conference.
Yeah. Thank you, everyone.